Welcome to Mountain Bike Physics Balancing Act Problem. An object in mechanical equilibrium must satisfy the following two conditions. The net external force must be equal to zero, and the net external torque must be equal to zero. We're going to look at that second aspect first. This is our mountain bike seesaw, and we're going to solve a problem in just a minute looking at the torques. The mass of the teeter-totter, or the seesaw, is distributed evenly on either side of the pivot point. So the torque exerted by gravity on the seesaw can be computed as if all the plank's mass is concentrated at the pivot point. Therefore, the torque that is the result of the plank would be equal to zero because there is no lever arm. That also means that the pivot torque would also be zero because there's no torque exerted by the pivot again because there's no lever arm. So the only torques that we have are the counterclockwise torque there on the left due to a weighted left end of that seesaw, and the two clockwise torques that will be on the right side, one due to a weight positioned at the end, and then the other one due to the bike as it moves from left to right and crosses the pivot point. At a certain point, the clockwise and counterclockwise torques are going to equal zero. The net torques are going to be equal to zero if we are going to be in equilibrium. Our problem is, what's the distance that the bike is going to travel from the pivot point to where our clockwise torque on the right is going to equal our counterclockwise torque on the left and bring us to equilibrium, where the net torque is equal to zero. So we're going to be looking for where is the bike going to be positioned to the right of the pivot in order to bring us to equilibrium. Any position past that point is going to favor the torque in the clockwise direction, and it's going to force the teeter-totter down, bringing the bike back to the trail surface. Let's start by drawing a free body diagram to represent what we see here in the mountain bike seesaw. All right, so on the left-hand side of this seesaw, we have a 20-kilogram mass that's holding this seesaw in position. It's 3 meters from the pivot point. On the right side, we have a 10-kilogram mass at the far end, also 3 meters from the pivot point. Remember that the teeter-totter itself is of uniform mass. It's 75 kilograms, and that 75 kilograms is going to be evenly distributed, so it's going to be all over the point of that pivot, and we're going to count that as zero torque. We know that the normal force is going to be pushing up, and our bike is going to transition to a position to the right of the pivot. That 100-kilogram bike and rider is going to exert a force due to gravity, and our job here is to figure out what is the distance that that bike has to be from the pivot point to allow for the counterclockwise torque on the left to be equal to the clockwise torque on the right. Let's label the mass on the left as big M, on the right as little m. Bike will be little b, the plank will be pk, and our pivot will be p. And we know that the second condition of equilibrium, the net external torques must be equal to zero, means that the torque of the big mass plus the torque of the little mass plus the torque produced by the plank plus the torque produced by the pivot plus the torque produced by the bike must equal zero. There's our free body diagram. Pause the video, read the story problem, and solve. Solution will follow. Solution for part A. Where to the right of the pivot should the bike be to balance the seesaw? First thing we're going to do is apply the second condition of equilibrium to the seesaw by setting the sum of the torques to equal zero. We know that net torque must equal zero for this seesaw to be in equilibrium. We've already established that the torque due to the plank and the torque due to the pivot are zero due to the fact that neither one of them has a lever arm. We know that the heavy mass on the left has a counterclockwise torque, the lighter mass on the right has a clockwise torque, and the bike will produce a clockwise torque as well. Our math sets up to look like this. The left-hand mass is 20 kilograms and it's positioned 3 meters from the pivot. Because all of our torques are produced by gravity, we can omit or neglect the need to put 9.81 meters per second squared in our calculation here. That will cancel, being on both sides of the equation. On the right side, our clockwise torques are produced by the 10 kilogram mass and the 100 kilogram mass bike and rider. Our problem is to solve for the meters that bike is from the pivot point. So 60 is going to equal 30 plus 100x. Subtract 30 from both sides. 30 will equal 100x. Divide both sides by 100. And our distance is 0.30 meters from the pivot point. Answer A. Now the solution for part B. Find the normal force F sub n exerted by the pivot on the seesaw. First thing we're going to do is apply the first condition of equilibrium to the seesaw, which states that the sum of all forces acting on the object must be zero, so that the object has no translational acceleration. Now, all of our masses here are accelerating in the downward or negative direction, so we know that our big mass times acceleration due to gravity, our little mass, our plank, and our bike are all forces in the negative direction, and the normal force of the pivot is going to be in the positive direction, and the sum of those has got to equal zero. To find our normal force exerted by the pivot, we're going to take 20 kilograms, 10 kilograms, 75 kilograms, the mass of the plank, and 100 kilograms, the mass of the bike and rider, and we're going to multiply it by 9.81 meters per second squared, which is acceleration due to gravity. And we're going to find our normal force to be 205 kilograms times 9.81 meters per second squared. And our answer to 3 significant digits (2.01 times 10 to the third newtons).